Welcome. Today, we are diving deep into something that powers pretty much every piece of software you use, but you might never see it: concurrency primitives. These are the secret building blocks, the fundamental rules of the road that keep our incredibly complex parallel systems from just descending into total chaos. So let's start with the biggest question of all. Think about it. How on earth do our computers manage to do millions, sometimes billions of things all at once without completely tripping over themselves, corrupting data, and crashing? It's kind of like managing rush hour traffic in a city of 10 million people, but for bits and bytes. And the answer? Well, it lies in a set of really elegant and powerful tools. So here's how we're going to break it all down. First, we'll cover the basic traffic rules for our code. Then, we'll meet the most fundamental gatekeepers. After that, we'll look at some more specialized tools for locking and counting before we switch gears to talk about coordinating entire workflows. We'll finish up by looking at the asynchronous future and, maybe most importantly, how you can choose the right tool for the job. All right, let's dive right into Section 1, Traffic Rules for Code. So before we go any further, we really need to define what these primitives actually are. At their core, concurrency primitives are basically low-level coordination tools. Think of them as the traffic signals, the stop signs, and the yield signs for all the different paths your code is taking at the same time. They're there to answer the really critical questions. Who gets to use this resource right now? How many threads can use it at once? And if it's busy, who has to wait in line and who gets the green light to go next? Okay, now let's meet our first set of tools, the basic gatekeepers. This whole section is about a core concept in computer science called mutual exclusion, which is just a fancy way of saying we need to make sure only one thing can happen in a critical spot at a time. And the most fundamental gatekeeper of them all is the mutex, which you'll almost always hear called a lock. Its job? Super simple. It makes sure that only one thread can access a shared resource at any given moment. The analogy here is absolutely perfect. It's like a single bathroom with just one key. If you've got the key, the room is all yours. Everyone else? Well, they've got to wait in line. It's really the simplest way to stop two operations from messing each other up. So where do you actually see these things? Well, they're the classic solution for protecting a piece of shared memory, for updating a simple counter, or managing an in-memory cache. But here's the really crucial system design insight. While locks are simple, they can create massive bottlenecks. That's what we call contention. When a whole bunch of threads are all waiting for that one key, your whole system just grinds to a halt. And that's exactly why, in big distributed systems, a simple lock is often the absolute last resort. Now, what if you don't have a resource that's like a single occupancy bathroom, but one that can handle a few users at once? Well, that's where the semaphore comes in. Instead of just one key, a semaphore has a whole pool of, say, n permits. The best analogy is a parking lot with 10 spots. The first 10 cars, they get in no problem. But that 11th car, it's stuck at the gate, waiting for one of the first 10 to leave and free up a permit. And this right here, this gets to the heart of why semaphores are so useful. They are perfect for something we call bounded concurrency. You're not trying to stop everyone, but you are trying to manage access to a limited resource. Think about something like a database connection pool, or when you need to rate limit calls to an API. You're controlling the flow. You're not just creating a single file line. Okay, so we've got our basic gatekeepers down. Now let's get a little more sophisticated and move on to some specialized locks and counters. These are smarter, more nuanced tools that are designed for very specific problems. And first up is the read-write lock. Now, this is a brilliant optimization. It's built on a simple observation. If threads are only reading data, they're not interfering with each other at all. So this lock allows tons of readers to access a resource all at the same time. But the moment a thread needs to write or change that data, it needs an exclusive lock, and that blocks all the readers and any other potential writers. The library analogy is perfect. Dozens of people can be reading books at the same time, but when the librarian needs to reorganize the shelves, everybody else has to clear out. And this chart right here, this is the money shot for a read-write lock. This tool is a high-performance beast only when your workload is super heavy on the reading side. If writes happen pretty often, you can actually get worse performance than with a simple mutex, because the writers can get starved out just waiting and waiting for all the readers to finish up. Next, let's talk counters. On one hand, you've got atomic variables. These are amazing because they use special hardware instructions to do simple things like incrementing a number without any locks at all. It's like a perfectly engineered turnstile that literally cannot make a mistake. You get instant, perfect accuracy. On the other hand, you have something like a long adder, which is designed for situations with just extreme contention.
Instead of one counter, it secretly uses a bunch of internal counters. It's like a giant stadium with dozens of entrance gates, each with its own little clicker. You don't get the exact total count in real time, but you get insane throughput. So you see the trade-off, right? It's instant accuracy versus high throughput scalability.
Okay, huge shift in thinking here. So far, we've really been focused on protecting data. Now, let's switch gears and talk about coordinating the workflow itself. These primitives aren't so much about guarding a variable as they are about managing the flow of tasks between different threads. And the king of this world is the blocking queue. It's a simple idea, a queue that solves the classic producer-consumer problem. Producers put items in, consumers take them out. But the real magic is in that word blocking. If a producer tries to add an item to a queue that's already full, it just waits. If a consumer tries to take an item from an empty queue, it waits too. The restaurant analogy is spot on. It's that ticket rail between the servers and the chefs. It naturally handles the flow of orders and stops either side from getting overwhelmed. It's an incredibly simple way to build systems that have back pressure awareness built right in. Now let's look at two tools that are all about getting threads to work together: the count latchdown and the cyclic barrier. Think of a count latchdown as a one-and-done deal. You set a count, say 5, and threads wait at this gate until 5 events have happened to count down the latch. Once it hits 0, the gate flies open and they all proceed. It's like the starting pistol at a race. It fires once and that's it, the race has begun. A cyclic barrier, on the other hand, is a reusable checkpoint. A group of threads all have to arrive at the barrier before any of them can move on. It's like a group hike where everyone agrees to wait at the trailhead and then again at the first scenic overlook before the whole group moves on together. So let's really break down how this works, step by step. First, individual threads start arriving at the checkpoint. As they arrive, they start waiting for the rest of their group. Then, once the required number of threads, all n of them, have shown up, the barrier trips. Finally, they're all released at the exact same time to proceed together. It's a really powerful way to enforce step-by-step coordination in complex parallel jobs. So we've talked a lot about waiting. Threads are always waiting for something. But what if you could achieve concurrency without waiting? Well, that brings us to our next section, and a totally different way of thinking, the asynchronous future. And this is where we get to talk about futures, or as they're sometimes called, promises. A future is basically a placeholder object. It's a promise that you'll get a result eventually. Instead of your thread just stopping and waiting for a task to finish, it gets a future back immediately and can go do other useful work. You just attach a callback function to that future that says, hey, when the result is finally ready, run this piece of code for me. The analogy is perfect. It's like ordering at a busy coffee shop. They give you a little buzzer or a number and you go sit down. You don't stand at the counter staring at the barista. When your order's ready, you get notified. This model is the key to building massively scalable systems because it eliminates idle threads just sitting around doing nothing. Whew, okay, that was a whirlwind tour of a ton of different tools. And that brings us to our final and honestly most important section, choosing your tool. This is where the real engineering and architecture comes into play. So after all that, which one should you actually use? How do you decide which one is right for your specific problem? Well, the answer comes from asking yourself the right questions. Is access to this thing truly exclusive one at a time, or can a few threads share it? That's your mutex versus semaphore decision. Is the contention on this counter going to be absolutely insane? That's your cue to think about a long adder instead of a simple atomic. Is your data read 100 times for every single time it's written? That just screams read-write lock. Are you trying to orchestrate a complex multi-stage dance, or just protect a single variable? That's barrier versus lock. And finally, the big one. Can you design your system to avoid blocking altogether? If the answer is yes, then futures are your best friend. And make no mistake, this isn't just some academic exercise. So many of the real-world performance problems, the bugs, the deadlocks, the systems that are mysteriously slow, they come from choosing the wrong tool for the job. It's like using a sledgehammer when you really needed a tiny screwdriver. Because at the end of the day, good system design means you design for contention. You don't just cross your fingers and hope it won't happen. By really understanding this toolkit, you are equipped to build systems that are not just correct, but robust and fast. If you can master these primitives, concurrency stops being this scary, complex thing, and it starts to feel like a superpower.